Hello and welcome to the EMC Live webinar, Updates to MIL Standard 461G. My name is Dawn Hoffman and I'm the Marketing Manager of Interference Technology, the creator of EMC Live. EMC Live is an online 3-day event hosted by Interference Technology. Featuring practical information and topics, this event will include roundtables, webinars, and videos on everything EMC related, and there's no cost to attend. Join us for our other webinars this week. This webinar is presented by Ken Javor. Ken has worked in the EMC industry for 30 years. He is a consultant to government and industry, runs a pre-compliance EMI test facility, and curates the Museum of EMC Antiquities. He is an industry representative to the tri-service working groups that write MIL Standard 464 and MIL Standard 461. He has published numerous papers and is the author of a handbook on EMI requirements and test methods. This webinar is sponsored by our platinum sponsor, Rohde & Schwartz. Rohde & Schwartz is one of the world's largest manufacturers of electronic test and measurement, communications, and broadcasting equipment. EMC and EMI test equipment and systems from Rohde & Schwartz determine the causes and effects of electromagnetic interference. For more information, visit www.emc.rohde-schwartz.com. This webinar is one of many. To check out our others, visit www.emclive2015.com. A recording of this webinar and downloadable PDF will be available on our website shortly. This webinar will be interactive. You will be able to ask questions and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box in the corner of your screen. If at any time you have a question, we ask you to type in the box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand and ask a question or report an issue, click the hand icon. We will present the topic for 35 minutes, followed by a 10-minute question and answer session. Now, Ken will begin the presentation.
Good morning. Welcome to a status report on the MIL Standard 461G revision process. This is a top-level look at major changes. We have a limited amount of time, so it's a high-level overview with a few deep dives into specific topics. Before we get into it, this is allergy season in the Tennessee Valley. I may be coughing, snorting, sniffling, coughing, and what have you. I'll try to mute if that happens. Apologize in advance. Okay. MIL Standard 461 is on a DoD-mandated 5-year review cycle. That does not mean a new revision has to be released every 5 years, just that a review must be performed to determine if a revision is necessary. Note that MIL Standard 461F was released in December of 2007, so the review cycle should have started in December of 2012. In fact, it did, with the first Tri-Service Working Group meeting being held then. But the second meeting, which was scheduled for April 2013, was postponed because of sequestration, and the postponement lasted a year. That's how we got to today. Final note, the 5-year review cycle imposed on MIL Standard 461D, 462D to make sure we didn't go 30 years again without a thorough review has resulted in a revision each cycle since then, which means that we have not yet perfected MIL Standard 461. Okay, so a little about your presenter. Major qualification is being an industry representative to the Tri-Service Working Group that writes MIL Standard 461 and having performed that function for the E through G revisions. Also having been in the business since MIL Standard 461A was the active revision, hence background pictorial. All right, abbreviated MIL Standard 461 background. It is assumed that if you're tuned in here, it means you work with the standard on a regular basis and are familiar with it. So just a little background, we all learned a long time ago it's more cost-effective to build EMC into equipments than to band-aid it on after integration. So this standard controls EMI characteristics of equipment and subsystems installed in DoD platforms. The standard also functions as a procurement spec for such equipments, but we all know it isn't a hard and fast pass-fail requirement as are other such standards such as RTCA DO 160 and standards governing equipment use in homes, offices, and industrial plants. The effect of having to meet stringent MIL Standard 461 requirements on the cost, weight, and scheduled delivery of equipment is taken into account when reviewing equipment MIL Standard 461 performance. So MIL Standard 461 is applicable to equipment installed in any platform acquired by DoD and also for ground equipment supporting it. Note that while we have standard setups for all requirements, There's no way those standard setups can accurately model what will happen in the wide variety of platforms operated by the DoD. Hence, MIL Standard 461 performance is often evaluated in light of how equipment actually operates in its intended environment. In other words, MIL Standard 461 quantitative performance is often evaluated for both quantitative and qualitative MIL Standard 464 performance. A few words about the review comment cycle. First of all, your inputs can make a difference. The MIL Standard 461F change in how the rod antenna is used was prompted by an industry review comment that was submitted in response to the MIL Standard 461F draft for industry review, which itself didn't even address the rod antenna at all. A few more words about the review comment cycle. The draft for industry review was released on 01 April, and comments are due by 18 May. By the way, maybe coincidentally, maybe not, the 01 April release reads MIL Standard 451G, and numerous people have commented on that, so there's no need to comment further on that one. In the past, Army, Navy, Air Force comments were submitted to their specific service, Tri-Service Working Group representative, and industry comments were submitted through a Tri-Service Working Group representative or through the SAE AE4 committee or the EIA G46 panel, but that's all changed. Now comments are filed electronically through a DoD website. Just follow the instructions on the slide to submit comments. This is not an automatic connection. Someone has to review your application and approve it, which takes a few days. So don't wait until the last minute. All right, the first change we cover here is an expansion on the previously existing electrical bonding section. This time or now requiring the measurement and recording of bonding or bond values prior to cable connection and any further testing. There are no test sample bond value requirements because bonding results must be in accordance with equipment-specific installation drawings and requirements, as always. Standard requires lisins to be bonded to the ground plane with a DC resistance of less than or equal to 2.5 milliohms. This addendum is just a standardization of what we hope everyone is already doing. So file this change under sad but true. In addition to the original wording in this section about keeping the test chamber clear of extraneous equipment and personnel, we now add the following. Remove all equipment and ancillary gear not required, including antennas, from shielded enclosures not being actively used for a particular subset of radiated tests. The fact that we put this in the standard is not a flattering portrait of the discipline, and it is just one example of several such addenda. On the other hand, at one time, 1964, it was thought this was a good idea for automating and streamlining testing. Now it's considered one of those things that just because it can be done doesn't mean it should be done. Times do change. All right, a really big change here, a really big addition. Major change to Table 2, controlling mission sweeps, accounting for and specifically facilitating the use of EMI receivers utilizing a time domain function. This is the use of a wide band, many megahertz or tens of megahertz wide, intermediate frequency amplifier to effectively process hundreds of frequencies simultaneously, greatly reducing test time. Not only does this speed up testing, but it allows better testing of devices whose cycle or on time is limited to periods shorter than those involved with traditional sweeps. An example might be a helicopter rescue hoist whose length of travel in an EMI test facility is a minute fraction of real usage. One issue with time domain versus traditional receivers addressed by the Table 2 change is intermittent signals with pulse repetition periods a significant fraction of the chosen receiver dwell time. Longer dwell times are required below 1 gigahertz to ensure capture of such low repetition rate signals. Above 1 gigahertz, it isn't really necessary because the original measurement bandwidth was already 1 megahertz. Now here can be seen the effect of the dwell time relative to the pulse repetition period. These plots are from the MIL Standard 461G Appendix Table 2 supporting material. The signal measured is a 10 microsecond long pulse with a 1 pulse per second repetition rate. The response of a traditional EMI receiver using the required 15 millisecond dwell time is shown in the upper left. The 15 millisecond dwell time results in a total sweep time of 10 seconds for this band, so 10 pulses are visible or almost all visible. The response of an FFT or time domain receiver also using a 15 millisecond dwell time is shown in the upper right corner. Because the total sweep time is the same as the dwell time, because the IF bandwidth is larger than the plot span and is shorter than the pulse repetition rate, the pulse was totally missed. It could have been captured since the dwell time of 15 milliseconds is longer than the pulse duration of 10 microseconds, but the probability of intercept proportional to receiver dwell time relative to pulse repetition rate, that is 15 millisecond dwell time relative to 1 second rep rate, which is a 1.5% probability of intercept, is not in our favor. Finally, at bottom center, we have an FFT or time domain machine's response to the same pulse stream when the dwell time has been expanded to 1 second, which is what's required in Table 2. The complete spectrum is captured, and it's immediately obvious it is a broadband signal. So this brings to mind an old nursery rhyme, and I beg your indulgence here, but there was a little girl, and she had a little curl right in the middle of her forehead. When she was good, she was very, very good, and when she was bad, she was hard. So the point of the Table 2 addition is to make sure that time domain measurements are very, very good and never horrid. So if you are unfamiliar with time domain machines, please read the appendix. Now, changes to general setups potentially affecting all the various requirements. A theme throughout this revision is a greater emphasis on physically large test samples, in addition to the Air Force's emphasis on avionics enclosure size devices. Test setups for larger items like 19-inch racks are covered. Just as until now, there have been rules for the number of antenna positions based on the width of the test setup, now there are supposed to be similar requirements for tall test items, and also for the length of cables required for large items. Cable length is addressed in the draft for industry review, but I didn't find wording on vertical antenna positioning for tall items. We talked about this at great length in the meetings, and I couldn't find it. So you all out there, look for it. Okay. MIL Standard 461 is somewhat unique in requiring end-to-end checks of measurement setups prior to each measurement. This is a much better approach than relying on routine periodic calibration of individual pieces of test equipment. The idea of this change is to de-emphasize formal calibration of passive transducers and even active ones that are routinely checked during every MIL Standard 461 test, and also easily checked using calibrated test equipment owned by an EMI test facility. So for instance, EMI receivers, spectrum analyzers, oscilloscopes, and electrically short field sensors are all items which must be routinely calibrated in a NIST-traceable manner. But items such as attenuators, cable loss, current probes, Listen impedance, even round antenna bases and low noise amplifiers are all easily checked in-house and are verified in each measurement system integrity check. Antennas can also be checked. It is important to note that checking a transducer's factor is not the same as calibration. So SAE Aerospace Information Report AIR 6236 contains guidelines on how to check transducer factors. It is not yet referenced in the draft for industry review because it has been voted on but not yet formally adopted by the SAE. It should be referenced in the actual release of 461G. The title is In-House Verification of EMI Test Equipment. It is not a calibration reference. The purpose is to provide a quick way to check a transducer's performance. If the performance matches recorded transducer factors, all is well. If they're significantly off, then recalibration and or repair may be indicated. All right. Table 4 from the draft for industry review shows the deletion of requirement CS106, bye-bye, and the addition of two brand new requirements. CS117 lightning-induced transients, which is borrowed from RTCA Deal 160, Section 22, and CS118 ESD, which is borrowed from RTCA Deal 160, Section 25, and also from IEC 61000-4-2. All right, an editorial change to all specific requirements is that frequency ranges have been removed from requirement section titles and relegated to the applicability subparagraphs where it more naturally belongs, because many frequency changes are many frequency ranges, are test sample or platform and or service specific. Now, Table 5 shows the applicability of each requirement. To be noted here is the applicability of the new CS117 and CS118 requirements, as well as some changes to existing requirements. CS117 induced lightning transient applicability is mainly to equipment performing flight or safety critical functions, and also to cables outside the protection of a metallic fuselage or wing. The CS118 ESD requirement applicability is universal. CE102. In addition to the CE102, measurement system integrity test is the only change to CE102. The reason for the change is because LISNs no longer require periodic calibration. The existing MIL standard 461E/F CE102 measurement system integrity check verifies LISN 50 ohm impedance at and above 2 megahertz, but not below. A minor tweak to the existing CE102 measurement system integrity check verifies the impedance below 2 megahertz as well. It does this by noting and controlling the amount of loading the LISN presents at 10 and 100 kilohertz, which is proportional to LISN impedance. NAVC for surface ships has made significant changes to the CE106 limit. The 5% frequency exclusion band gets expanded for high power transmitters, but the limit becomes much more stringent for very high power transmitters. The limit is now fixed instead of relative. That is, no longer specified as dBc, but simply dBm, which means that the higher power the transmitter, the more stringent the limit. All right. CS101. CS101 adds the option of monitoring injected ripple in the frequency domain using a spectrum analyzer or EMI receiver instead of an oscilloscope. A device known generically as a power line ripple detector, or PRD, provides an isolating interface between the power bus and the input to a frequency domain receiver. This provides a big advantage when test sample powers AC. The PRD was developed and commercialized after MIL standard 461F was released, and thus it is not mentioned there. A picture's worth 1,000 words. A movie showing CS101 ripple riding on an AC power waveform is even more expressive. Now, one issue never controlled by CS01 or CS101 was the injected signal dropping across the power output impedance instead of across the test sample. This is a simple voltage divider that's proportional to the relative impedances of the power source and test sample. If the power source impedance is a significant fraction of the test samples, then there can be a problem. This is not addressed in the main body of MIL standard 461G, but is mentioned for the first time in the appendix. The PRD provides the functionality to quickly check if excess signal drops across the power source. Now, this is a specific comparison of monitoring injected ripple at 800 Hertz on a 400 cycle bus. On the right, a cursor marks the peak amplitude of the 800 Hertz CS101 injected signal, and is obviously very clearly visible and easy to read. On the left, well, once again, a movie's worth 1,000 words. Now, prior to 1993, the CS01 frequency range was 30 Hertz to 50 kilohertz, regardless of whether applied power was AC or DC. After 1993, that is after the after MIL standard 462D was adopted, use of the Solar Electronics 7021-1 phase shift network was forbidden, and as a result, it was impossible to monitor ripple injected at frequencies below the power frequency. The power line ripple detector makes it possible once again to monitor below the power frequency, and it is just as easy and no different than at frequencies above the power frequency. On the left, cursor is placed at the peak of the 100 Hertz injected CS101 signal on a 400 cycle power bus. On the left, one can see the low frequency amplitude modulation of a higher frequency carrier. It is impossible to gauge the modulation depth on an oscilloscope. However, there was no real interest in bringing the AC requirement back to starting at 30 Hertz. Had this little device been available in 1993, we never would have lost this spectrum. CS106 is deleted. Bye-bye. The stated purpose of CS106 was to prevent power line transients from cross-coupling between power wires and low-level signal wires when equipment design did not segregate the two, as is often the case with new submarine designs that don't have a dedicated power connector and also use press-on flex cable wiring between a connector and motherboard. However, measurements showed that coupling between adjacent traces on flex cabling from a CS106 transient looked very similar to what CS115 would couple, so that there was no need for the separate requirement. All right. A fundamental change to CS114 takes it back to the way it was under Mill Standard 461D, 462D. Some background is necessary, and this is an important change because it becomes much more stringent on shielded cables at low frequencies. This slide portrays the physics of electromagnetic field-to-wire coupling. It shows why the limit increases with increasing frequency when the wire is electrically short and then reaches a plateau. The equation represents the coupling of potential to a transmission line, and the drawings are a qualitative explanation. The upper drawing is samples taken of a sine wave. The middle drawing has shading proportional to the amplitude of the sample sine wave. In the upper drawing, where darker means higher amplitude. Various lengths of transmission lines are superimposed on the shaded background. It can be seen that looking at the shortest transmission line, lengthening it captures more power from the sine wave in proportion to the increase in electrical length. This is the same thing as saying that the sine of a small angle equals the angle and explains the 20 dB per decade linear increase in coupled potential when the cable is electrically short. But once a transmission line is a quarter wavelength long, adding increasing length adds proportionately less increased signal with extension. More signal is captured, but it is diminishing returns. This marks the departure from linear increase with increasing length in the bottom drawing. And once the transmission line is a half wavelength long, any further increase in length actually decreases coupled potential because the sine wave amplitude has changed sine. So once a cable is a half wavelength long, the coupling at that point marks the maximum that can be coupled. And after that point, the coupling just oscillates between the maximum and minimum as a function of electrical length. A plateau has been reached. When an electromagnetic field impinges on or illuminates an electrically short wire above a ground plane, then the currents induced depend on the wire termination impedances because the inductive reactance of the cable itself is low. With 50 ohm loads on both ends, the cable impedance is 100 ohms around the loop until the reactance takes over, hence the calibration fixture used for the test. If a cable has an overbraid, or lacking such it is made up of many shielded pairs or triplets, the impedance of the cable is just the inductance of the loop formed by the cable shields above ground and the shields terminated to ground. In the plots above, the constant field intensity from 10 kilohertz to 30 megahertz illuminates a 1 meter long wire, which is 1/10 wavelength at 30 megahertz, so an electrically short wire over the entire frequency range. With 50 ohms at each end, the performance on the left is obtained, and one can see the near 20 dB per decade increase in coupled current, the superimposed dotted line, with noise floor at the low end and the beginning of transmission line effects at the high end providing the departure from the dotted line ideal. This represents the current to be established in the calibration fixture. However, when the same field illuminates a wire shorted to ground at both ends, as on the right, then the coupled current versus frequency behavior changes markedly. This is because the increase in field-to-wire coupling efficiency is offset by the inductive reactance of the wire or cable increasing at the same rate. This results in flat coupling of current versus frequency when the cable is electrically short. If the pre-calibrated forward power is the sole limiting factor when performing CS114 testing, then the induced current on a shielded cable provides the exact same behavior as electromagnetic field to wire coupling, as opposed to the present practice of limiting current under such conditions to 6 dB above the calibration fixture current limit. The result is a test that is much easier to perform and a more accurate model of reality. Now, the graph at the upper right is borrowed from A. Smith's seminal work on the subject of the coupling of external electromagnetic fields to transmission lines, and it shows the same behavior for high and low impedance terminations. The book was published in 1977, so we're not breaking new ground here. And again, it should be noted that this change makes for a much more stringent test for low impedance cables at low frequencies, so keep that in mind as you review the standard. Another CS114 change is to require the measurement of induced current when performing the forward power pre-calibration. This ensures that the current probe transfer impedance is properly accounted for in the test software or data reduction. Note that it requires an extra calibration fixture. All right, new requirement CS117. Lightning is not a new requirement for DoD platforms, but it is being included in MIL Standard 461 so as to eliminate the need to separately call out a non-DoD standard. It is borrowed from RTCA DO 160, Section 22, and care was taken to do things the same way. In the draft for industry review, no pin injection is required, just like or keeping in philosophy with CS114, CS115, and CS116. We don't expect a lot of clamor to add pin injection, but feel free to have at it. Levels don't exceed RTCA DO 160, Section 22, Level 4. Requirements include multiple stroke and multiple burst. If a test facility has a Section 22 lightning capability to Level 4, they can perform the MIL Standard 461 version. There's no new test equipment necessary. CS118, the second new requirement, is personnel borne electrostatic discharge. Applicable to electrical, electronic, and electromechanical subsystems and equipment which does not interface with or control ordnance items. Aside from that caveat, applicability is universal, just like C102, CS101, CS114, and RS103. It is a brand new core requirement. The test method and equipment is leveraged from industry ESD standards, RTCA DO 160, Section 25, and IEC 61000-4-2. The ban definition is from RTCA DO 160, Section 25. The target is from IEC 61000-4-2. Once again, if a test facility has a capability to perform these tests, no new equipment is necessary. Levels are from 2 kV to 15 kV. Levels below 15 kV are default contact discharge. 15 kV is air discharge. 8 kV is the ordinary requirement. 15 kV has to be specified by the procuring activity. Rise times about 1 nanosecond, requiring an oscilloscope with single event bandwidth near 1 gigahertz. Now, moving on to RE102. There were 3 changes discussed for RE102, one of which appears in the draft for industry review. There is a strong desire to either replace or at least augment the 461F rod antenna setup with one not requiring grounding of the coaxial transmission line directly below the rod antenna base. Because many test facilities don't have a low impedance ground connection at convenient locations. Also, a fully isolated rod antenna and counterpoise is desirable from an accuracy standpoint. This is not in the draft for industry review. 2 methods of obtaining isolation are transformer and optical. Transformer is a petty cache modification, but to date there are issues with transformer performance. Optical works, but is expensive. Second issue, typical rod antenna whips in the past have been quite thin, and the old standard assumed value of 10 picofarads was a useful approximation. There are rod antennas on the market now with rod diameters approaching a centimeter. For these, 15 picofarads comes closer. The standard takes cognizance of this by stating that the manufacturer's suggested value should be used. Last issue. It was discussed in meetings that freestanding or any test sample whose vertical extent is larger than the prescribed antenna beam width requires multiple vertical antenna positions, just as always been the case for horizontally extended setups. This was supposed to be in the standard, but I have yet to find it. So it may be in there, but it's escaped me so far. Now then, 3 things you don't want to see made: sausages, legislation, and EMI standards. So file the next few slides under TMI, too much information. This is all about trying to isolate the rod antenna. There are, by the way, now optically isolated rod antennas, but that's not what this is about. The 461F rod antenna setup change detuned a known resonance condition. It is desired to completely remove the resonance rather than just detune it, both for improved measurement accuracy and to eliminate the requirement to ground the coax transmission line below the antenna base. The resonance is a parallel LC trap consisting of counterpoise capacitance to ground and the coaxial transmission line shield acting as an inductive ground connection. One or the other or both of the LC components must be eliminated to eliminate the resonance. One way to fix that is to use the floor of the shield room as a counterpoise, but that isn't practical. The test setup would also have to be on the floor. Another way is to eliminate the inductive bond strap. That can be done either via an isolation transformer or an optical connection. As previously noted, an isolation transformer is cheap but problematic, while an optical interface works but is expensive. And I should note, just in passing, that I think later today there is one of these little webinars specifically about a brand new optically isolated rod antenna, which would be perfect for this kind of work. But anyway, yet it is not mentioned in the standard. Okay, next slide here. Transformer testing looked at existing models. It may become necessary to design one specifically for this application, but that would not support the MIL standard 461G release schedule. So test setup description for evaluating the transformer isolation. A wire above a tabletop ground plane is driven from a 50 ohm source through attenuation at both ends to minimize VSWR in the coax cable due to impedance mismatch. The wire is less than 1 meter long, so no loss and no VSWR and constant potential versus frequency. Hence, the electric field due to it must also be flat versus frequency because this is a quasi-static field measurement. The theory may be found in a 2011 item article about the 1.04 meter rod antenna. In the following measurements, the output of the rod antenna is compared to the potential on the radiating wire using a network analyzer. The antenna has a flat antenna factor over the test frequency range of 10 kHz to 30 MHz. Therefore, we are looking for a flat frequency-independent transfer function. So, MIL standard 461E results, sort of. Not exactly MIL standard 461E because the counterpoise is not connected to the tabletop ground plane and in fact is at a lower level than the tabletop for MIL standard 461F. But the coaxial connection responsible for the resonance is for MIL standard 461E. Resonance is clearly visible, departing from nominal by over 30 dB. Now, MIL standard 461F results. The MIL standard 461F setup reduces the overall magnitude of the resonance due to the ferrite bead detuning the high Q phenomenon. Maximum departure from nominal is just over 10 dB, but is now bidirectional. Note, detuning only happens if the inserted 20 to 30 ohms is mainly resistive rather than inductive, a clarification needed in 461G. Many people have criticized the 461F configuration because they added nearly pure inductance to the cable. Not surprisingly, adding inductance to an LC trap doesn't help matters any. Now, isolation transformer approach, first iteration. A mini circuit's $50 isolation transformer. Nice little $50 transformer, very nice performance. Isolation transformer approach Rev B. An Allen Avionics isolation transformer with similar published specs to the mini circuits model yields slightly different performance. But both transformers look good compared to MIL standard 461F, at least in this test result. Summary sheet. The two transformers don't give exactly the same results, but they are closer to flat than MIL standard 461F, which itself was an improvement over mill standard 461E. Looks pretty good here, but Wright-Patterson Air Force Base gets different results. They saw a very narrow and very high-level resonance using the mini-circuits part. The mini-circuit transformer used at Wright-Patterson Air Force Base had 3 times the inner winding capacity as the unit used at EMC compliance. Also, the Allen Avionics model had 10 times the inner winding capacitance of the mini-circuits part used at EMC compliance. Inner winding capacitance clearly must be controlled, although it is not spec'd off-the-shelf models. Issues unresolved and unfortunately not yet ready for prime time. Okay, next topic, RE103. The same NAVC changes apply for RE103 that were made to CE106. The frequency exclusion zone being transmit power dependent above 1 kilowatt and a fixed transmit limit. RS103. Nav Air has greatly extended the default frequency range of the test. It was 100 megahertz to 18 gigahertz. Now it's 2 megahertz to 18 gigahertz. Now all services have a core frequency range of at least 30 megahertz to 18 gigahertz, and some services and platforms go lower. Now, a grandfather clause that existed in Mill Standard 462D through Mill Standard 461F above 1 gigahertz, allowing pre-calibration of the required field intensity instead of real-time leveling, has been eliminated. Above 1 gigahertz, it was previously acceptable to place a double ridge guide horn at the place test sample would be situated and record the power required to achieve the required field strength and then play that back during testing. In 1993, there existed electrically short field probes working to 18 gigahertz, but they were new and expensive, and a desire to minimize the cost of the new standard resulted in this grandfather clause, allowing test facilities without the latest equipment to be able to perform to the new standard. A survey performed in 2014 of EMI test facilities across the USA showed that every single facility queried had probes operating to 18 gigahertz, so that the elimination of the grandfather clause at this time would not be an economic hardship. The driving reason for the elimination of this section was not technical but legal. Practitioners of EMC law, as opposed to EMC engineering, were twisting the wording of the standard to argue that the grandfather clause applied below 1 gigahertz as well as above. This is counter to the wording and philosophy of the standard, and it was deemed that the easiest way to stop this abuse was to eliminate the field precalibration entirely. And that concludes the summary. We're now open for questions. Thank you.
Thank you, Ken. We would like to have a call for final questions. Please enter any last questions you may have in the navigation pane at this time. We do have one asking if the new revision G addresses RE testing in the reverberation chamber, and if yes, what about the tuned mode versus stirred mode testing?
We did discuss reverberation testing for radiated emissions, but we were not satisfied that something existed, excuse me, that we were willing to put in standard at this time. And that's a very good question. One of the issues is, in my mind, okay, and now I'm speaking as Ken Javor, not in representing anybody else, because when you're doing susceptibility testing, you have to have a dwell time sufficient for the test sample to respond, which our default value is 3 seconds. That would clearly require the paddle to hold steady for that amount of time. But for radiated emissions testing, if you allow the spectrum analyzer or EMI receiver or say the time domain receiver to go as fast as it can in a calibrated manner, what you will find out is, excuse me, that you can sweep much, much faster because the amount of time you need to dwell at any one frequency is just 1 over the bandwidth. And so for RE102, it's like, 100 kilohertz bandwidth, that's, 10 microseconds and so on and so forth. The point is, what I'm getting at is that if you have a paddle that's constantly moving at 6 to 7 RPM, the amount of time it takes to, say, sweep the entire biconical range, the paddle's basically stationary. And so if you do one complete rotation at 6 or 7 RPM, what you'll find out is it's the same thing as, and I'm going to say this in max hold mode, it's the same thing as just sweeping over and over and over again and catching every possible emission from that device in every possible orientation, meaning the reverb setup. The point is that you don't have to step and dwell. You can actually just let that thing rotate at a slow speed, and because of the fast or the short amount of time you have to dwell at any one frequency, it's equivalent to being mode stepped or mode tuned as opposed to just sweeping. I hope I was clear on that one.
Great, thank you. So another attendee asks, when does issue G become mandatory for USDOD applications?
Well, I mean, all I can give is a programmatic response. Once G has been released, okay, and that's sometime later this year, then obviously it applies to contracts that are let after the effectivity date of G. So if you get a new contract between now and when G is released, it'll still be referring to Rev F.
Okay, then the next question is CS 114, 115, and 116 applicable for handheld radios? Because it seems these are for more devices connected to a platform.
Well, in order for those three requirements to be applicable, cables have to, be attached to something because, they're cable tests. So if a handheld item, had maybe a wall wart connection to power, well, CS 114 would apply to that connection. But if it's totally handheld, in other words, if it's just operating in battery mode and it's just a box with an antenna, then there would be there's no way to do those tests.
Okay, great. We are actually running up against time. We did actually receive a number of good questions. So we will address those later and have those answered at a later date. If you would like to get more information, you can go to our website at emclive2015.com, or you can email us at info@interferencetechnology.com to specify what you need, and we can direct you accordingly. Please join us for EMC Live 2016, which will take place in April of 2016. And to the webinar attendees, if you have any more questions that we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website, interferencetechnology.com, and emclive2015.com. We will also send a link to all participants shortly. Thank you for attending.